These are the typical tap conditioning filters that are here. And, picture the block diagram of the tap of where this is plugged into. All taps are pre-installed with just a jumper net in that slot. So it's just a through, as if there's no conditioning filter. You could remove that jumper and put in a cable equalizer. A cable equalizer filter shape has more loss, and this is the slope of the frequency response. More loss at lower frequency, less loss at higher frequencies, and these are typically used in low value taps, and we'll explain this a little bit more detail. Cable simulators is very similar to the name. It's simulating cable loss, so it's less loss at lower frequencies, higher loss at higher frequencies. These are typically used in higher value taps. There's devices called return path attenuators, and these are diplex units. There's the diplex inside that little plug-in filter where the return can be configured to have more attenuation than the downstream band and the forward band. And there's also what we call the high tap filter, where you have a diplex where the forward band is attenuated more than the return band. But we do not recommend using diplex versions. As we mentioned previously, system designs can change, and you may migrate your sub-split diplex to a mid-split or a high split or no splits or whatever changes in your diplex filter. You would have to actually go to all these taps to figure out which one has a return path attenuator in that and remove that and change it. So that return path attenuator can be used, as you can see, it's a similar shape as a cable equalizer, except without a diplex. It's a straight line. And a high tap value filter can be used as a cable simulator. So we do not recommend using these two diplex versions. We just recommend using cable equalizers or cable simulators in modern designs.
Right. So note to technicians, if you've recently upgraded your system to a mid-split or a high split, and you're having difficulties with a customer of locking on or acquiring those new upstream channels, it's possible that you may have a tap that has one of these return path or high tap filters in them, which is a diplex device. So to Neil's point, you may either have to replace the tap altogether or to replace that plug-in component with a jumper or something else to allow that customer to lock onto those new activated upstream channels.
So we're first going to talk about cable simulators, and cable simulators are used in high value taps. And we talked about the highest value tap we see today is a 23, but long time ago there used to be taps as high as 32. But to illustrate this example of why cable simulators are used, I'm going to just explain a 32 value tap for this example. So this is before you put a conditioner in, and at the output of the node you have a high upstream tilt. And you have if you have a 32 dB tap here, you got to keep in mind the cable modem, this is 32 dB on both upstream and downstream, 32 dB of loss. So the cable modem needs to be transmitting at a very high level to overcome that 32 dB. So in this case, it could be transmitting as high as plus 49 dBmV, high transmit level in this modem. So if I put, instead of that 32 dB tap, I use a 23 tap and a cable simulator with a 9 dB cable simulator, you're actually adding 9 dB to 23 dB for the forward band downstream. You're simulating a 32 dB in the forward, but I'm only having 23 dB in the upstream. This way, the cable modem only needs to overcome 23 dB, and the transmit level can go down to a more reasonable plus 40 dBmV upstream transmit level if you use a cable simulator in high value taps.
Very useful in today's networks, particularly as we increase the upstream bandwidth. And we won't really talk about power today, but amplitude and power are related. So the more bandwidth that you have, the modem's transmit ability can only output so much power distributed across a wider portion of spectrum. So managing your upstream path losses through equalization or other types of conditioning is very, very important.
The other type of plug-in conditioner we talked about is a cable equalizer. This is used in low value taps. So here's a drawing of what it would be for a network before you put conditioning in. And they're using low end taps at the end of the line, low value taps. So here you have a very large negative tilt from going down the coax. The tilt going into this tap could be going down like this. And because it's a low value tap, the modem is transmitting at a much lower level. There's very little loss in the upstream band at cable modem. Let's say it's a sub-split, you're transmitting at 20 some megahertz. There's very little loss on coax there. You're only going through 8 dB of loss here, so the transmit level at this cable modem is quite low. So you have excess negative tilt, low transmit modems, and low value taps. And because low value taps, ingress from these homes are attenuated 8 dB, so much of the ingress in a network comes from low value taps, and this creates a degraded signal to noise, carrier to noise in your network. But simply adding in a cable equalizer, a 10 dB equalizer in the low value tap here, one plug-in, you can create a positive tilt here, and you increase that upstream attenuation by 10 dB. So you're making the modem transmit 10 dB higher. So now we're transmitting at plus 40 dBm in a sweet spot. And it kind of does two things. It's a twofold increase. It transmits higher level and also makes the upstream 10 dB more attenuation, which reduces ingress from those homes by additional 10 dB. So it's like a twofold improvement. Signal to noise ratio improvement from better transmit levels and blocking ingress in homes as well for cable equalizers.
Not to mention adding positive forward tilt to your downstream.
Yes, correct.
So looking at just those two examples at the highest value taps and the lowest value taps, effectively you can negate the negative consequence of the attenuation that comes naturally from coaxial cable to ensure that your customer experience is much more uniform, right, and that you have the same quality and level of signals in both the upstream and the downstream at every tap, regardless of the tap value.
Yes. Yep.
So fantastic.
I just got one other quick little slide just for an example. I'm going to look at a typical design to show a modem with low transmit power and how to cure them. How do we provide better tilt? How do we improve signal to noise? So you have a whole cascade here, and I'll go through this very quickly. This is sort of a busy slide. You have a node output level, levels of 55 and 860 megahertz, of plus 10 dBmV at 55 megahertz, plus 18 dBmV at 860 with a certain tilt. These are the different levels of different taps and upstream modem level at each of these homes, assuming a certain amount of cable loss. So you can see from the lowest value tap to the highest value tap is 16 dB, 24 tap down to an 8 tap. But the transmit levels at each of the modems varies from 41 all the way down to 30 dBmV. So it's an 11 dB delta in the modem transmit level. You want to keep your modem transmit level as uniform as possible, keeping your transmit power in the sweet spot. There are some low transmitters and high transmitter volume, so you do not want to use those. So making two adjustments just at the end of the line, and you put a cable equalizer 4 dB and a cable equalizer 10 dB in that same cascade, you just increase the upstream modem level to 40 dBmV in these two homes, and You made the max to min transmit level vary from 41 to 37, only a 4 dB delta, with just a couple plugins in the whole network. You've cleaned up multiple issues with just a couple plugins for tap conditioning. But keep in mind, this is not a tool for technicians to use to troubleshoot. Follow the design on the print. It's designed for whatever plugin to use.
So it is important to understand, some of the symbology too, right? So
Yes.
on the map here, between 1902 and 1904, those two premises, there's a 23/8 value tap, and the plugin for that tap would be a 12 value cable simulator. And then we've got a pretty long span, it looks like, of 6 1/4 P3 cable going to a 24 tap. And that looks like it has a Cable Simulator 9 plug-in into it. So as we're looking to troubleshoot or to, look for impairments or sweep and balance, it is important to know that the passive plugins do have an impact on the signals coming out of the port. But that it's also important to measure on the seizure mechanisms themselves, as we talked about before, using an impedance match test probe, so that we can properly measure the performance of the tap itself, and include the impact of the plugin, whether it be a cable simulator or a cable equalizer.
Great, well said. So yeah, I hope that was a very good overview of passives in the network. Yeah, it
was fantastic, Neil. I thank you for your time. We are recording between Christmas and New Year's, so we're both on vacation. But this was one that we've been talking about doing for a couple of months now, and I was really looking forward to getting this material put together for our viewers to help people understand the importance of passives, how they work, why they do what they do, how they're measured, and how they're quantified. The things like the insertion loss, the return loss, the port-to-port isolation, those are all important things that I think may be undervalued in terms of the passive devices' impact to the network, how they influence design, and why they're designed in the way that they are. So I can't thank you enough for taking time out of your holiday schedule to spend some time with our members and viewers and helping us to understand passives a little bit better. So Neil,
enjoyed it
thank
very
you very
much.
much.
Glad to be part of this, and hope everybody got something out of the presentation.